Hi, I'm Ken Greenbaum on the Display and Color Technologies team. Thank you for attending this high dynamic range rendering with EDR talk. It is a technology I am thrilled to be sharing with you. Let's quickly run down what we'll be covering and who might best benefit from attending. We will start with what EDR actually is, describe the 4 steps used to add EDR to your existing app, discuss the native EDR API for more control of rendering, and finally, we will explore a series of best practices related to EDR. Now, what is EDR? EDR is an acronym you might not be familiar with. It stands for Extended Dynamic Range. We use EDR to refer to both the HDR representation and the HDR rendering technology used on our platforms. It is somewhat akin to color management, which you might already be familiar with. Developers of many types of apps will find this talk interesting. To begin, any developer interested in computer graphics technology, high dynamic range displays, and especially the new XDR displays that Apple has been releasing over the last couple of years. Next are hardcore game developers who want to create the most realistic and exciting experience, unlocking bright details that might already be present in their rendering engine. Critically, there are the pro app developers who are interested in achieving studio reference response for HDR video and still images. Finally, there are developers of apps whose emphasis isn't specific to graphics, but who would like to embrace the HDR still image and video content now entering the ecosystem. HDR is here, and it is enabled by our EDR technology. As we will be discussing, we have displays with incredible capabilities already in users' hands. Stunning HDR content in the ecosystem that users are capturing, streaming, and downloading, as well as HDR apps, both games and professional, available in the App Store. EDR is an adaptive technology. As we will discuss, EDR not only maps HDR content to displays of wildly different capabilities, but also supports an even wider range of viewing conditions. Have you ever noticed displays look much different in a bright environment versus when viewed in the dark? The bright, vibrant colors you experience indoors likely look dim and muted with low dynamic range when viewed outdoors. The display didn't change. At a given brightness setting, it is always making the same light. It is the environment that changed, as well as your vision that rapidly adapted to the environment. In a dark environment, your vision adapts to the displayed content, the predominant source of light. But in a bright environment, the user's vision largely adapts to the environment over the much dimmer display, causing the content to look dim and washed out, crushing blacks and shadow detail. This is why EDR and the underlying ambient adaptation technologies dynamically adapt display parameters such as white point, black point, reference white brightness, and dynamic range that we describe as EDR headroom to map the display to the user's adapted vision. EDR's adaptation provides a number of benefits. Perhaps most surprisingly, this results in EDR creating a true HDR response even on conventional standard dynamic range displays. That is, when those displays are viewed in dimmer environments with correspondingly dimmer brightness settings. Similarly, EDR's dynamics produce a situation-optimized HDR capability on bright HDR displays. This allows HDR content to look stunning in HDR referenced dim environments, while providing a reduced but optimal dynamic range in brighter environments, all while preserving shadow detail, such as the patches on this illustration. EDR rendering is supported on most devices we've shipped for years now. We describe HDR capability in terms of EDR headroom, which is how many times brighter than the conventional maximum SDR white the brightest EDR pixels can be rendered to the display. EDR headroom varies based on display capability as well as other parameters, including the current brightness slider setting. On conventional backlit displays, as found on most recent Macs and iPads, up to a very noticeable 2x SDR is available. iPhones with XDR display provide up to an exciting 8 times SDR EDR headroom. The new iPad Pro's Liquid Retina XDR display has up to an incredible 16 times SDR. Roughly 5 times SDR is provided when driving typical external HDR10 displays via Mac, iPad, and Apple TV. And the Pro Display XDR renders to a jaw-dropping 400 times SDR in the default XDR preset when brightness is set to the minimum 4 nit value. Not only are HDR-capable displays already in many users' hands, but HDR content is becoming mainstream. In addition to commercial HDR content, users are adding HDR still and video content captured on their own iPhones and other devices to the ecosystem. An awe-inspiring list of applications have already adopted EDR. Top-tier games supporting EDR include Baldur's Gate 3, Divinity Original Sin 2, and Shadow the Tomb Raider. A growing number of Apple TV services provide HDR content, including TV app, Netflix, and YouTube. Finally, an exciting and growing list of Pro apps have adopted EDR, both upping the ante and increasing the amount of HDR content developed on the platform. Affinity Photo, DaVinci Resolve, Cinema 4D, Final Cut Pro, Nuke, and Pixelmator Pro are just some of the apps. We chose to name our technology EDR in part to differentiate it from HDR, which tends to mean different things to different people. When many think of high dynamic range, they imagine bright displays capable of producing deep blacks. The production-minded may think content formats, perhaps HDR10 or Dolby Vision. To the technical, it brings transfer functions like PQ or HLG to mind. And perhaps to the artistic, HDR can even suggest the surrealistic painterly tone map, representing bright highlights as well as dim shadow detail as SDR. Consider this SDR tone map of an RIT-produced ultra-high dynamic range OpenEXR image. In the tone map, the glowing light bulb and the shadow detail are all present. However, the dramatic dynamic range of the original HDR image is lost. EDR is not a painterly HDR to SDR conversion, preserving all details while losing the intention, but rather a true high dynamic range rendering. The RIT team combined the 18 bracketed digital SLR exposures seen here to create their HDR image with its amazing 500,000 to 1 dynamic range. EDR fully represents this in floating point, with the image's subject, the Luxo lamp itself, as pixel values under reference whites 1.0, and with brighter details, such as the emissive orb of the light bulb, represented as values approaching 500. That's 500 times brighter than the lamp base. EDR's implementation creates a mapping between the reference whites of every element of the system, from the reference white of the content to that of the display, through to that of the user's adapted vision. This mapping is fundamental to providing many of the benefits of EDR, including allowing HDR and SDR content to coexist side by side, optimally exposing an HDR display's dynamic range across environments, even allowing conventional SDR displays to render true HDR, while always allowing EDR to render as great a dynamic range as possible. For instance, on a Pro Display XDR, with brightness sliders set to the maximum 500 nits, EDR values up to 3.2 will be rendered without clipping. Brighter elements, such as the lamp head with correspondingly greater EDR values, will clamp to the display's 1600 nit peak. Lowering the display's brightness setting toward its 4 nit minimum, occurring when in a dim to dark environment, either automatically via auto brightness or manually using the brightness slider, EDR values up to 400 become renderable, thereby delivering most of the dynamic range of this exceptional image. The image's brightest elements, while still rendered to the display's 1600 nit peak brightness, now clearly define the light bulb's contour. Similarly, other details are revealed, such as the colors of the brightly illuminated color checker. With the user's vision now adapting to the image's 4 nit reference white, the image's brightest elements are now amazingly rendered 400 times brighter than the lamp base. Let's explore the implication of EDR's floating point HDR representation and rendering pipeline. Being floating point, EDR can represent every color that humans can perceive, as represented by this completely filled chromaticity diagram. Similarly, EDR can represent brightness that would be damaging to eyesight if fully rendered. As such, EDR's representation is future-proof. As mentioned, EDR is not only a representation, but is also an HDR rendering pipeline. EDR is an extension to the color management technologies that Apple pioneered and has been shipping for a very long time. For instance, GPU-accelerated color-managed video first shipped way back in macOS 10.4 Tiger. Conceptually similar to allowing media of normal and wide color gamut to be displayed side by side, EDR allows HDR and SDR assets to share the screen in a harmonious manner, as well as to be appropriately rendered to displays of differing capabilities. Among other things, this means that developers may continue to use existing SDR assets and selectively add EDR support as needed. Let's explore visually EDR's representation of HDR pixel values. EDR is a floating point representation. EDR 0 represents black. 1.0 represents SDR max, also known as reference white or UI white. Thus, EDR 0 to 1.0 represent the SDR range, the same as always. These values represent the subject of an image and will never be clipped when rendered. EDR values beyond 1.0 represent values exceeding SDR brightness, such as highlights and emissive surfaces. These values might get extraordinarily bright and, while representable, are subject to clipping when rendered. EDR is used to drive the display, no matter if the display has a conventional pure power response or a newer HDR transfer function. Let's consider Pro Display XDR in the default XDR preset, which is PQ-based. EDR 0 drives the display to 0 nits via the 0 nit PQ code. EDR 1.0, called reference white, is scaled by the display brightness slider, or auto brightness, the same as always. The XDR preset has the typical about 4 to 500 nits reference white brightness range. Let's consider the maximum 500 nits setting for this example. Regardless of the brightness setting, the peak white is always 1600 nits in this preset. Thus, EDR max, the brightest renderable EDR value, is 3.2, as can be calculated by dividing the 1600 nit peak white by the 500 nit reference white. Correspondingly, we say there is a 3.2 times SDR headroom, as the brightest value renderable to the display is 3.2 times brighter than the reference white. In summary, on Pro Display XDR, using the default XDR preset, with display brightness, also known as reference white, at 500 nits, EDR values 0 to 3.2 are rendered to the display as 0 to 1600 nits, with EDR 1.0 displayed as 500 nits. Finally, EDR values above EDR max's 3.2 are clipped to peak white 1600 nits. Amazingly, as display brightness is reduced toward the minimum 4 nits, EDR values up to 400 become renderable, thus exposing incredibly bright details at their true dynamic range. Now that we have an overview of how EDR works, we'll explore adding EDR to your application. There are 4 steps to add EDR support to most applications. These steps are all straightforward, however their effects can be subtle, and you likely won't reliably have EDR results until you apply all of them. First, you have to request EDR by adding an attribute to the appropriate context, layer, or object. Second, you have to associate an extended range color space with your buffer, layer, or app. Color management will clip EDR values beyond 1.0 if an extended range color space is not specified. You should know that color management might only engage when the source and destination color spaces don't match, so this clip might be intermittent or content dependent. Third, you need to select a pixel buffer format that can represent values above 1.0. This is usually some form of floating point. Finally, your application must generate pixels that exceed the SDR 0 to 1 range, and thus have sparkly elements to show off. Many developers have existing apps to which they might want to add EDR support. Perhaps the easiest way to get started with EDR is to simply substitute HDR video or still image content in place of existing SDR content. Then follow the 4 steps we just outlined. Some applications, for instance the email app shown, might selectively enable EDR only when HDR content is encountered. AV Foundation's AV Player interface supports a growing number of HDR video formats, such as Dolby Vision, HDR10, and HLG. AV Player will automatically render these formats as EDR when possible, on all platforms except for watchOS. Existing AV Player-based applications don't require any changes to render supported HDR video formats via EDR. Let's look at an EDR-enabled AV Player code example. As always, one simply first creates an AV Player instance using AV Player's player with URL. However, in our example, we specify HDR video content. Next, add the player to a layer using player layer with player. Finally, point the controller to the player and request the player to begin playing. AV Foundation will automatically perform what is required to render the HDR media as EDR, and will enable and disable EDR based on the content type. HDR video playback is pretty straightforward. Next, let's consider HDR still image rendering. Image.io has extensive support for HDR image formats, and conveniently will return the decoded pixels as EDR in floating point buffers. While Image.io is available on all platforms, presently the decoded results may only be rendered as EDR on macOS. We will demonstrate how to incorporate Image.io-based assets into an application in the upcoming CA meta layer example. Now, let's explore the native EDR API. As I mentioned, the native EDR API was created for applications like games and pro apps, where the developer may want to render custom content and have more control over how HDR media is rendered. Presently, this API is available on macOS via CA meta layer and NS-OpenGL View. Let's look at an example using CA meta layer, the preferred native EDR framework. To begin, we're going to look at the first 3 of the 4-step process: opting into EDR, setting an extended range color space, and selecting an FP16 pixel buffer format. First, opt into EDR by setting the meta layer's once extended dynamic range content attribute to yes. Second, set the meta layer's color space to an extended range color space, such as extended linear display P3. Third, set the meta layer's pixel format to a floating point format, such as RGB A16 float. Next, we will examine the 4th EDR opt-in step, actually generating EDR pixels. In this case, we will use Image.io to import HDR still image content and render the result as an EDR texture. It is a little involved, so we will walk through it step by step. We create the CG image from HDR content, draw the decoded image into a floating point bitmap, create a floating point texture, load the EDR bitmap to texture, and finally, render the texture to the EDR-enabled metal pipeline. First, the CG image is created from the source specified in HDR image URL using CG image source create with URL and CG image source create image at index. Next, create the CG context with CG bitmap context create using the same color space we set earlier on the meta layer, and draw the EDR image into the floating point context using CG context draw image. Now we create a floating point texture of type RGB A16 float using new texture with descriptor. Load the EDR image data using CG bitmap context get data into the EDR texture using replace region. Finally, the developer is ready to render the EDR texture into their EDR-enabled metal pipeline and enjoy the dynamic results. For those still supporting OpenGL-based applications, we will explore enabling EDR on NS-OpenGL View using similar steps to those we've already demonstrated. Adoption of EDR might also provide the opportunity to fully embrace color management. However, we will not cover that in this talk. We will explore the following steps: opting into EDR, selecting a floating point pixel buffer format, and drawing EDR and content to the NS-OpenGL view. Setting an extended range color space is not required, as NS-OpenGL view is not automatically color managed. First, opt into EDR by setting the NS-OpenGL view's once extended dynamic range OpenGL surface attribute to yes. Second, set the pixel buffer format to NS-OpenGL PFA color float with color size 64. Finally, draw EDR values into the OpenGL view, run your modified application, and enjoy the results. Now that we've discussed enabling basic EDR support in existing applications, let's dive a little deeper and explore a number of best practices to get the most from your EDR-enabled application. Recall EDR opt-in step 4 is to set an extended range color space. And in our example so far, we explicitly set an appropriate extended range color space. However, many apps don't set their color space explicitly and instead use the default color space provided by the framework. This often corresponds to the display or composition space, which are not extended range, thus breaking EDR unless something is done. Let's explore an example of how to promote existing color space to extended range. First, get the existing color space, in this case from your view's window. Second, promote that color space to extended range using CG color space create extended. Finally, assign the newly generated extended range color space to the window, buffer, or layer as appropriate, enabling apps that don't explicitly set their color space to use EDR. Next, we will explore best practices for generating EDR content. So far, we've mentioned EDR content has values that exceed 1.0, but not how to actually synthesize this content or convert it from HDR sources. Please be careful generating EDR content, or it's possible to experience the dreaded glowing bunny syndrome, or content may have an eerie, iridescent glow that makes properly authored content look dim in comparison. As has been emphasized, pixels above EDR 1.0 should only encode specular highlights and emissive surfaces. This means that it is inappropriate to take SDR content and stretch it to be HDR. SDR content is compatible with EDR as is in its native 0 to 1.0 range. This aligns the SDR reference white to that of HDR contents. When HDR content is authored to be too bright, with what should be dimmer elements or even shadows exceeding EDR 1.0, it will appear unnatural compared to well-authored content. The user's vision may begin to adapt to this overly bright content, making other content appear dim in comparison. Please consider this example of a girl holding an 18% gray card as used by photographers and animators to set exposure. The girl is the subject of the photograph, and consequently, the photographer or animator will set the exposure so that she is at or below reference white, and thus will not be clipped. Most user interface elements shouldn't exceed EDR 1.0 as well. However, there may be exceptions, including EDR color pickers or temporarily scaled UI, brightly illuminated to capture attention. Emissive surfaces such as the sun or clouds, as well as specular highlights, such as the sun reflecting off a shiny surface, are potentially far brighter than reference white, and consequently are expected to exceed EDR 1.0. A scene's brightest elements are already clipped by SDR encoding. Consequently, SDR content is correctly represented as EDR 0 to 1. Sometimes a workflow will require HDR formats to be converted to EDR explicitly. As mentioned, Image.io decodes HDR content to EDR, requiring no further conversion. For instance, HLG is decoded to the 0 to 12 EDR range, with EDR 1.0 representing reference white. Image.io decodes other HDR still image formats to their own particular ranges, with EDR 1.0 always corresponding to the source's reference white. AV Foundation does not presently decode HDR formats, such as HDR10 to EDR. Consequently, these need to be adapted for use with EDR rendering. This conversion is straightforward and involves two steps. First, converting to linear light by applying the inverse transfer function, and second, dividing by the medium's reference white, for example 100 nits for PQ content, so that reference white will be mapped to EDR 1.0, and the maximum PQ 10,000 nit value will map to EDR 100. Consider this photograph that, like many photos, both digital and film, has the sky clipped to white. While EDR will never clip values up to EDR 1.0 reference white, which represent the subject of the image, EDR will clip values above reference white that are beyond the current EDR max, and thus are not able to be rendered on the current system display and display settings. These values above reference white are highlights or emissive surfaces, such as the clouds, sky, and sun, that we can't see in this image, and as such are usually okay to be clipped. However, clipping of bright details is not always acceptable. For instance, consider this image of a sunlit airplane flying high above the clouds. Notice the blue HDR11 livery? Brightly illuminated, the number, as well as the fuselage it's painted onto, might both be rendered at greater than reference white, and hence potentially be clipped depending on the display capabilities and the current EDR max. If this number was a crucial plot element in a film or game, then dynamic tone mapping may be employed to avoid or manage clipping and keep the number visible. Let's explore how sophisticated applications may stay abreast of the current EDR max value and accordingly adapt what they render. Applications may want to subscribe to NS screen notifications, perhaps to adjust the brightness of objects in the scene, change the scene's exposure, apply a bloom effect, or even soft clip to ensure critical details are not lost. Presently, there is only one dynamic EDR value accessible from the NS screen interface. It is maximum extended dynamic range, color component value, and represents the current maximum renderable linear EDR value. As we have stated, EDR values greater than EDR max will clip to EDR max, and EDR max may dynamically change since it is dependent on characteristics such as display brightness or true tone that may themselves change over time. The two other EDR values accessible from NS screen are static, meaning they won't change over time. In contrast to the preceding value, maximum potential extended dynamic range color component value returns just that, the maximum EDR linear pixel value that might be renderable without clipping on this display. That is, if the display brightness and other features were set appropriately. Max potential EDR may be used to guide decisions, such as if SDR or HDR versions of content should be used, or even deciding if it is worthwhile to enable EDR at all. Please remember that potential is in the name. The current maximum renderable value, EDR max, might be below this value. 1.0 is returned for displays or display presets not supporting EDR. The final static value, maximum reference, extended dynamic range, color component value, is mainly of interest to pro application developers concerned about achieving the highest fidelity to a reference standard. It provides the maximum EDR value that is guaranteed to be rendered without distortion, such as clipping or tone mapping on a given display. 0 is returned on displays that do not support reference rendering. Now, let's explore example code that reads EDR values via NS screen. Here we read the two static EDR values, max potential and max reference. EDR values may be different across displays, so be sure to make the call on the screen your app is actually on. In this example, we are using the NS screen associated with your window. The application may keep abreast of dynamic EDR changes by subscribing to NS window did change screen notification. Then query the current EDR parameters upon receiving the screen changed event and potentially altering what is rendered based on knowledge of the current EDR headroom. To complete our discussion of tone mapping, we will briefly explore the CA Meta Layer Tone Mapper. This is of interest for pro apps that author and render HDR video, such as HLG and HDR10, to project-based HDR mastering parameters. System apps, as well as apps employing AV Player, as we've already described, use the CA metal layer tone mapper to provide media-specific optical-to-optical transfer function and soft clip for HDR values that would otherwise not be renderable. The CA metal layer tone mapper is enabled via the CA EDR metadata attribute and is available on macOS. This example demonstrates how to enable the system tone mapper by setting the EDR metadata attribute on your app's CA metal layer. A number of EDR metadata constructors are available. They are specific to the HDR video standard as well as the mastering information provided. Here we see the HLG metadata constructor, which takes no parameters. Next, we demonstrate one of the HDR10 constructors. This one takes 3 parameters: explicit minimum and maximum luminance, both in nits, as well as optical output scale, which is often set to HDR10's 100 nit reference white. Once constructed, set the resulting object on your application's CA metal layer, causing all content rendered on this layer to be processed by the system tone mapper based on the provided metadata. Closely related to adaptive tone mapping, an app may want to draw with the brightest white currently renderable. We already understand how to get the current EDR max from NS screen. However, EDR headroom is a linear value, and pixels are most often non-linearly encoded. In this final example, we will convert EDR max into the app's potentially non-linear color space. First, we use CG color space create with name to create the linear EDR max white pixel we want to render, and then convert the linear EDR max pixel to the application's color space using CG color create copy by matching to color space. The resulting color may then be used in any EDR-enabled application. This leaves us with one last topic to discuss: the power and performance implications of EDR. Similar to all CG rendering, evaluating EDR's impact on power and performance can be complicated and often depends on the specific hardware architecture and display technology used on a given device. While we won't go into details in this talk, there are some general points to consider, such as producing brighter pixels often consumes more power. Floating point buffers used with EDR may be larger and thus consume more bandwidth than the fixed point buffers that might otherwise be used. This in turn correlates to more power consumed. Even enabling CA EDR metadata-based tone mapping involves an extra processing pass. This in turn increases latency and bandwidth. Simply, EDR, like many features, isn't free, and as such, it should be used judiciously. The best practice is to enable EDR when there is both HDR content and potential EDR headroom available. Disable EDR when this is not the case. Similarly, choose HDR or SDR versions of content to open or stream based on if the EDR potential headroom or even the current EDR max headroom is significantly greater than 1.0. Or, more simply, only enable EDR when the user will see the difference. We've covered a lot about EDR in a short period of time. I hope that you are as excited by EDR as I am and are eager to integrate it into your applications. To summarize, EDR is used on macOS, iOS, iPadOS, and tvOS devices. EDR is an extension to the color management and SDR representations you are already using. EDR is easy for applications to opt into. EDR is compatible with industry HDR standards and provides a non-modal adaptive experience across devices and environments. Please check out the following talks and resources for more information on HDR video playback, Apple Pro Display XDR, and metal rendering of EDR. Thank you. Hope you enjoy the rest of your WWDC.